Imagine a busy highway where many cars want to reach the same destination. If every driver tries to go as fast as possible all the time, the road quickly gets jammed and accidents happen. The same thing can happen inside a computer network. Many computers try to send data at once, and if they do it without any rules, the routers become overloaded and packets are lost. Congestion control in TCP works like traffic lights and speed limits. It makes sure the amount of data, the cars, on the network is kept at a level the network can handle, preventing traffic jams and ensuring everybody reaches the finish line safely. When a TCP connection starts, it does not know how big the network pipe is, so it begins very cautiously. It uses a variable called the congestion window, CWND, to decide how many packets, usually measured in MSS maximum segment size, it may send without waiting for an acknowledgement. At the very first round time, RTT, it sets CWND equals 1 MSS. After each successful RTT, it doubles the window. CWND equals 2 MSS, then 4 MSS, then 8 MSS, and so on. Mathematically, after KRTTS without loss, CWND equals 2 to the power of K times MSS. This exponential growth is called slow start because, despite the name, the window grows very fast, just like a child carefully testing how many stairs she can climb before stepping back, then taking larger steps once she feels confident. The fast growth of slow start cannot continue forever. The network pipe has a finite size. TCP uses a threshold called SS thresh, slow start threshold. When CWND reaches SS thresh, TCP decides that it has likely found the safe size of the pipe and switches to a gentler mode called congestion avoidance. Think of it as a child who, after reaching a safe height on a ladder, the threshold, stops jumping 2 rungs at a time and instead climbs 1 rung at a time to avoid falling. SS thresh is usually set to a large value at the start, often the receiver's advertised window, and is reduced after a loss event, guiding future transitions between the two phases. In congestion avoidance, the window grows much more slowly each round trip time. The sender adds only 1 maximum segment size to CWND additive increase. If a loss is detected, CWND is cut in half multiplicative decrease. The rule can be written as CWND equals CWND plus maximum segment size per round trip time additive increase. CWND equals CWND divided by 2 when loss occurs multiplicative decrease. This pattern is called additive increase multiplicative decrease, abbreviated a IMD. Imagine a child filling a bucket with water. She pours a small steady spoonful additive each time. The bucket is not full, but if the bucket overflows, she empties exactly half of it before continuing. A IMD gives the network a smooth, fair way to share bandwidth among many flows, because each flow increases slowly, but backs off quickly when it detects trouble. TCP can notice a lost packet in 2 main ways. The first is receiving 3 duplicate, a CKS called triple duplicate, or 3-dup, a CK. This means the receiver got a later packet but is still waiting for an earlier one, so it repeats the CK for the missing packet 3 times. When the sender sees those 3 duplicates, it immediately cuts CWND to half the same as in a IMD and retransmits the missing segment. This is called fast retransmit. The second way is a timeout. If no CK arrives for a packet within a calculated period, the retransmission timeout RTO, the sender assumes the packet or many are lost and resets CWND to 1 MSS, restarting slow start from scratch. Think of the child on a swing. A quick push duplicate a CKS makes her pause and swing a little slower, while waiting too long without any push timeout makes her stop completely and start again from the beginning. Real implementations use some default numbers. RFC 6928 recommends starting with an initial CWND of 10 MSS for modern high-speed links, giving a gentle burst that is still safe. SS thresh is usually set to a very large value, often the receiver S advertised window at connection start, and later reset to CWND divided by 2 after a loss. RTT is measured by timing how long a segment takes to travel to the receiver and back. To make the estimate stable, TCP uses an exponential weighted moving average, EWMA. Estimated RTT equals 1 minus alpha times estimated RTT plus alpha times sample RTT, where alpha is typically 0.125. This smooths out occasional spikes, much like a child averaging the time it takes to run different lengths of a hallway to guess how long the next run will take. Explanation: for TCP Reno, a widely used version of the algorithm, the average throughput T can be approximated by the well-known formula. T approximately equals MSS divided by RTT multiplied by the square root of 2p over 3, where p is the probability that a packet is lost. Suppose MSS equals 1460 bytes, RTT equals 100 milliseconds, which is 0.1 seconds, and the measured loss rate p equals 0.01, which is 1%. Plugging ins. Square root of 2p over 3 equals square root of 2 times 0.01 divided by 3, approximately equals square root of 0.0067, approximately equals 0.082. So T approximately equals 1460 bytes divided by 0.1 seconds times 0.082, approximately equals 1460 divided by 0.0082, approximately equals 178 kilobytes per second, approximately equals 1.4 megabits per second. This calculation shows how a small increase in loss dramatically cuts the achievable speed, which is why congestion control must keep loss low. The model helps engineers predict how a new link will behave before they actually send data. Many versions of TCP have been created to improve performance on different networks. TCP Reno adds fast recovery after a triple duplicate, so the connection does not restart from slow start each time. TCP New Reno fixes a subtle bug in Reno's fast recovery when multiple packets are lost in one window. TCP cubic used by Linux grows CWND according to a cubic function of time, allowing much faster growth on high delay, high bandwidth paths. Think of a child who can now take bigger steps after learning the ladder is sturdy. In the real world, devices often negotiate which version to use during the three-way handshake. The most common default today is cubic on modern OSes, while older devices may still use Reno or New Reno for compatibility. Understanding each variant helps network engineers choose the right settings for data center, links, satellite connections, or home broadband.